Hello everyone, this is Xincheng, and I'm presenting VirtualNexus Enhancing 360-Degree Video AR/VR Collaboration with Environment Cutouts and Virtual Replicas. This work is situated in the area of AR/VR telepresence. Past research has identified a trade-off between depth-based reconstruction and 360-degree video. Environment reconstruction, such as point clouds, allow users to virtually move around and interact with the scene with depth perception. However, as shown in the image on the left, depth-based environment reconstruction often suffer from imperfect depth scanning, such as holes and occlusion. In comparison, 360-degree video delivers a virtual scene with a higher visual quality, such as in the image on the right. But with depth perception, 360-degree video telepresence is less interactive. To add to the 360-degree telepresence interactivity, prior work has implemented basic interactive modalities such as pointers and annotations. The interactivity of 360-degree telepresence can be further extended by locomotive robots. However, apart from the hardware overhead, attaching to a remote user's viewport to a moving proxy can lead to simulator sickness. Finally, past work has allowed users to toggle between point cloud views and 360-degree views. However, such an approach requires users to frequently adapt to different sets of interactive modalities. We present VirtualNexus, a system that enhances the interactivity of 360-degree AR/VR telepresence. We contribute coherent interactions in 360-degree telepresence without the need to context switch. We enhance access to the remote environment with environment cutouts, and we enhance the access to individual physical objects in a remote scene with 3D replicas. To start, let's watch a video of how VirtualNexus functions. VirtualNexus supports a local AR user and a remote VR user to collaborate in a telepresent experience. In the local environment, we use a 360-degree camera and align the remote worlds with a QR code attached to it. We implement basic functionalities such as synchronized annotations and shared virtual objects. We further enhance the remote telepresence with environment cutouts. Here, the remote user duplicates the whiteboard and pulls it closer. As the remote user pulls the whiteboard close to them, the local user sees the remote user's avatar move towards the whiteboard, enhancing the collaborative experience. By pulling an environment cutout close, the user can have a close-up experience to the area of interest. The cutout works as a world in miniature and synchronizes the user's operations to the original world. After sketching the bar graph on the whiteboard, the users decide to visualize the bar graph in 3D on that desk. So the remote user pull that out and start to create 3D visualization with virtual primitives. In the meantime, the local AR user can scan around the physical objects to create virtual replicas. The virtual replicas become shared virtual objects users can spawn from the menu. Here, the users are using the virtual replicas of the toys as legends on the 3D bar graph. So now here is an overview of VirtualNexus system architecture. On the AR side of our system, the local user wears a Microsoft HoloLens 2 and streams the environment with an Insta360 camera. On the VR side of our system, the remote user wears a Meta Quest VR headset wired to a desktop. In the video pipeline of our system streams the 360-degree video in real time and synchronizes the VR head and controller pose for video transcoding and avatar rendering. Our system also has a virtual replica pipeline. The AR headset sends the RGBD images of the object scanned by the local AR user to the virtual replica server, which runs instant NGP to create virtual replicas. The created meshes are sent back to both the AR and VR side. Finally, Our system synchronizes the virtual objects, annotations, and spatial mesh in a peer-to-peer fashion. Now we can dive into more details of the system design of VirtualNexus. We organize the key features of VirtualNexus with the key challenges that motivate the system designs. The first challenge VirtualNexus set out to solve is to ensure a coherent interactive experience while utilizing the merit of both 360-degree video and reconstruction. In our system, we embed and align a 3D reconstruction with the 360-degree video. As the main medium of delivery, 360-degree video provides a high resolution, while the embedded 3D reconstruction provides the illusion of physical presence. Virtual objects follow physical rules as they interact with the telepresence physical world. Without relying on a locomotive robotic proxy, 360-degree telepresence fixes a remote user's position in telepresence. So this is the second challenge our system sets out to solve, with environment cutouts. Instead of having users walking in the space, we allow users to point an area of interest close to them. To do so, the user starts with defining the area of interest with 4 points. These 4 points and the camera position forms a pyramid frustum. Our system intersects the hidden depth mesh with this frustum and duplicates the intersected triangles to create the environment cutout. As a remote VR user activates the environment cutout, we continuously transform their avatar to the selected area of interest in the AR world, enhancing the collaborative awareness. For example, as you can see here, as the remote VR user on the left is pulling the cropped whiteboard closer to them, the local AR user sees their avatar move toward the whiteboard in the physical world. The environment cutouts function as synchronized worlds in miniatures. The manipulations on these components are synchronized to the original scene in VR and the physical environment at host side. For example, here you can see as the VR user annotates and moves objects on the whiteboard cutout, the annotations and the virtual objects shows up in the original whiteboard in the VR world, as well as the local physical world. The final challenge we tackle in 360-degree telepresence is the lack of access to remote physical objects. VirtualNexus allows the local host to ad hocly scan an object with their AR headset. The system then replicates the object with InstantNGP. We create a mesh of the neural rendering generated by InstantNGP, allowing both the remote and local users to create and interact with them. Here is the results from each step of our pipeline. The AR user centers the original object in their field of view and scan it. We then perform background segmentation on images sampled from the scanned video. With the photos and the corresponding camera pose, we create volume rendering of the object in InstantNGP. We then mesh the object with cube merging and colored vertices, and produce the final result smoothed with voxelization. We now show a set of example application scenarios. In this first example, we show how users can collaboratively prototype a virtual scene with VirtualNexus. Here, the two users use preloaded primitives and scanned objects to create a scene where characters travel through a forest. VirtualNexus can also be used for remote education and instruction. Here we show how a remote student can go close to a whiteboard to answer a math question. Alternatively, the local instructor can create virtual replicas of physical items and ask the remote guest to follow along with them. The third potential application of VirtualNexus is shared recreational activities. Here we show a pair of users utilizing the floor as the bowling alley. To evaluate our system, we recruited 7 pairs of participants to collaboratively design and prototype a whiteboard. After they complete the task, the participants answer questionnaires on the experience. In particular, we asked about the system's effectiveness, immersion, and how the participants perceive each other's presence. The questionnaire is in 5 Likert scale, and we gathered qualitative feedback about their answers to each question. Here we summarize the main takeaways. Both the AR and VR users found the virtual replicas useful and aids the efficiency of communication and prototyping. On the AR side, the participants found the presence of the remote guest well perceived. A key contributing factor was that the AR user could see the VR user's avatar translated to their active workspace as showcased in the bottom right image. On the VR side, users found VirtualNexus to provide a sense of physical presence, and in particular, when the annotations and objects react to the remote environment physically. The VR participants also found the environment cutouts to be intuitive and effective. Some of them pointed out, as the cutouts can be put closer, it provides better precision and clarity when accessing a further region. For future work, we plan to investigate the interactive modalities necessary if scaled to more users. Secondly, in our current implementation, as the VR user is translated to the AR user's view, the VR user still sees the AR user from the 360-degree camera's perspective. In our study, we found that this creates a misalignment of awareness between the users. Future work can tackle mitigation to such misalignment. Finally, we will attempt to adopt neural rendering as the main medium to present the remote environment, and research the corresponding interactive modalities in such a system. This brings us to the end of this presentation, and thank you. We welcome any questions.